Hello and welcome to our video on describing and analyzing data, otherwise known as measures of center, measures of dispersion, and measures of relative standing. So we're going to look at all of the basic numerical descriptors of data, such as, like I said, measures of center, standard deviation, which is a measure of spread, and percentiles, which is a measure of relative standing. Well, I think we're all familiar with the mean, or what we normally call the average. If we're dealing with a population, then you add up all of your data values and divide by capital N, where capital N is the number of data values in your population. And you can see that that is listed with the Greek letter mu for mean. However, when we're doing it for a sample, it's done the exact same way. We add up all of our numbers, divide by how many have, but now the number that we have is designated with a lowercase n. Instead of the Greek letter mu, we just put x bar. Anytime you see Greek letters, that's always going to represent a parameter that was computed from a population. And anytime you see non-Greek letters, right, our standard alphanumeric stuff, Arabic letters, those just represent regular stuff from a sample. So for instance, we have this sample of 6 days from employees at an insurance company. And from those 8 pieces of data, we can find the mean by adding them up, divided by 8, and getting 8.9 after we round. And we can see that on average, they miss 8.96 days. I'm assuming this is per year. So roughly 9 days per year for that sample, which is why it's an X bar. The median of a data set is the middle value, but you first have to arrange them from smallest to biggest, otherwise it wouldn't make sense. Now, the value of this average, sometimes people think of the average of the data set as being the median instead of the mean. That's not really what is normally done. The mean is really what everybody thinks of as the average. What they're trying to say here is sometimes if your data is severely skewed, the median is a better indicator of the center of your data or the middle of your data or the average of your data, right? It's supposed to be in the middle. So that's kind of where that's coming from. So here's another set of data. First, we have to put it in ascending numerical order, i.e. from smallest to biggest. Since there are 12 pieces of data, the median is going to fall right in between the 6th and the 7th, right? So we've got 1, 2, 3, 4, 5, 6, and then here's our 7th. So the median's in between those two, and whenever it lands in between two, you take their average. If it landed on something, so if we had like a 13th data value, then 7 would be the middle because it would have 6 below and 6 above, and the answer would just be 27.1. But since we have an even number, it's in between the two, we take the average, we get 27.05. The mode is the data value that occurs the most frequency, mode most, right? So something like this, when we have a bunch of words, all we can do with words is calculate a mode, but we can also do modes with numbers. In this case, violet occurs more often than any other color. So the mode is violet, and since we only have one mode, we call it unimodal data, right? So it can be unimodal, bimodal if you have 2 modes, and then multimodal if you have 3 or more modes, and then you can also say it has no mode. Here's another example with football jersey numbers, and because each of them show up exactly once, there's no mode. Then we look at the ages of children at a playground, and we can see that both 4 and 7 have a frequency count of 3, which is more than anything else. So it's bimodal with 2 modes of 4 and 7. Now, very quickly, if you put this data into a TI calculator and ask for the mode, it will just give you the smallest one. If you put this data into Excel and ask for the mode, it will just give you the smallest one. You have to then, in Excel, use the more advanced function mode.multi, and then it looks for multiple modes, and then it will report both. So just be aware of the limitations of the technology you're using. Here's another example. You can see that we've got 2 10s, 2 13s, 2 9s, 2 14s. Everything shows up twice. So what are the mode? Well, some people would say all of them, and those people would be wrong. It's a really easy mistake because, well, everything showed up twice. But remember, the mode has to be the most frequent. And since nobody shows up less than 2, then 2 isn't the most, it's the least. It's, everybody's the same. So there would be no mode in this. Now, of course, if we came along and we added, a 15, then these would all be modes because 15 only showed up once. It's that kind of thing. Now, an outlier is a data value that is extremely different from the rest of your data values. It just doesn't play nicely with the rest, right? It's that oddball that's, a lot larger or a lot smaller than everything else. How do we calculate outliers? Well, we'll get to that in a second. In the beginning, we just kind of visually see whether or not something's an outlier. Like you look at this set of data and you go, well, maybe 84 is an outlier because it's a lot bigger than everything else. Maybe 11 is an outlier because it's a lot smaller. But then again, we've got a 15, a 14, a 15, a 16. So 11 is probably not a problem. The other big number is 61 and then a 44. So 84 is seeming like it could possibly be an outlier, but we'd have to compute it. All right, add everything up, divide by 11 because there's 11 numbers. We get 37.4 as our mean. Put them in order. Find that 26 is the middle because remember we have 11. So we have 5 below, 5 above, lands right on a number. So that's our median. We also look for, repetition, which I always think it's easiest to look for repetition when we put it in order. We can see there's 2 15s and nothing else, right? So we've got a mode of 15. Now, all three of those measures of center, mean, median, and mode, they're called measures of center because they're supposed to give you an idea of the center of your data, i.e. the average of your data. So all three of them can be thought of as types of averages. Obviously, the mean is the typical average that we think of. I mean, that's literally what, a mathematical average is calculated the same way as a mean. However, the median is directly in the middle of your data. That can also be thought of as an average. It's not a great one. And then the mode can also be thought of as an average because the most frequent data values are usually in the middle of your data, but they don't have to be. Now, in the case of this, you only have 15 only show up twice in a set of 11 numbers. That's not frequent enough to think of that as the average. And in fact, if we see numerically, it's nowhere close to 26. Okay. Pause the video really quick and see if you can calculate the mean, median, and mode for that set of data. Did you get these? Hopefully you did. And remember, depending on your technology, it might not give you both. So sometimes you have to visually find modes. Order everything and just look for them. The range is simply the difference between the largest and smallest values. So all you have to do is get the maximum, subtract the minimum from it, and that gives you the range. That's usually pretty easy. And again, technology will do all these for you. So the easiest thing to do is put it in order, like you're trying to find the median, and then do the difference between the max and the min. So to find the range of those, that's all we got to do is find the max and min of each, subtract them, and get our answers. They end up both being 49. Lo and behold, it's a nice little happy experiment or circumstance or whatever you want to call it. The standard deviation is a measure of how spread out your data is. And the formula is a little complex, and it's not something I would want you guys to try and do by hand more than once or twice just to understand, what the calculations do, because it gives you a better understanding of what the actual standard deviation is if you calculate it a couple times by hand. So it's a good idea to get yourself a nice little small set of data with a nice even mean. Like make sure that you manipulate the data enough so that the mean is a whole number, because you don't want to be dealing with decimals. It just makes the math a big pain in the butt. And then you can do this formula. Once again, Greek letter, right? That's a sigma, Greek letter. So we know this is the standard deviation of a population, right? Capital N, population, mu, the mean of the population. And then if we're doing the standard deviation of a sample, which is normally what we're doing because we normally don't have data from a population, we have an S instead of sigma. We have X bar for our mean, and we have little n. You might also notice that it's n minus 1 instead of n, right? So the formula actually shifts a little bit when we're taking the sample standard deviation. And that's because the standard deviation is what's called a biased estimator. It always underestimates the population standard deviation. So in order to counteract that, in the formula, we augment it and make the bottom number n minus 1, which makes it a smaller number. And when you divide by a smaller number, right, you get a bigger result. So it helps kind of undo that systematic underestimation. So we can calculate our standard deviation by first calculating the mean, then use that mean to calculate the other bits and pieces. So here's what we would do if we were doing it, in steps in Excel. We would write down our data values. Then we could just set this up as equals this cell minus the mean, which in the case of our numbers was, remember, 20.67. And then you could just drag that down and it would populate all those. Then the next step is you have to square it with it. So this would just equal this thing squared. Drag it down, get all those. The next thing you have to do is sum them all together, right? Because if you remember, this means the sum of each data value, right? X sub I means each data value, subtract the mean from it, square it, and then sum all those up. So that's what we've done to this port. And then all that's left is dividing by n minus 1 and then taking the square root. So the next thing we do is we take that 96.01, we divide by n minus 1. There's 9 pieces of data, so we divide by 8. We get this. We take the square root of it, and we round, and we get 3.5. You should do that a couple times just to see what it's doing, just to understand what it's calculating, because you can see that, it's taking each value, it's subtracting the mean from it, so it's giving you the distance from the mean. Then it's squaring that, it's adding them all together, it's dividing by how many you have, roughly, and then taking the square root. Well, you can think of the square root as kind of undoing the square. So it's really taking the sum of all these differences and dividing by how many we have. Doesn't that sound like an average? Yeah. So it's basically giving us, right? It's basically telling us that on average, this data value is about 3.5 years different from the mean of 20.6. So any particular piece of data you picked, on average, it's going to differ from the mean by 3.5 years. Now, obviously, some differ by more, some differs by less, but on average, that's how different they are from the mean. That's what a standard deviation tells us. Now, you can use your TI-84 to do all this stuff. So, for instance, you bring in a TI-84, right? And to do these, you would go stat. Well, first, you got to make sure you turn it on. Stat. And then right here, you just hit enter, because you want to edit, and then you put all your data into a list. So I put all of this data in list 1 already. Once your data is in your list, it's really simple. You just quit out of this, you always go back to the home screen, go back into the stat menu, and now arrow over to calculate, and you want to calculate one variable statistic, so you hit enter. And then you got to tell it what list you want to calculate it on. It defaults to list 1. And so you can just go down here to calculate, or if you have an older one, you just hit enter to tell it. And then here you go. Here's my average. Here's a bunch of stuff that it just gives you in case you want to calculate other things. Here's S of x and sigma of x. Remember we talked about sigma of x would be the standard deviation if this was a population, S of x if it's a sample. Since this is a sample, we would use the 10.3. It also gives us number of things, and if we scroll down, it gives us the minimum, gives us Q1, which we'll talk about later, gives us the median, gives us Q3, and it gives us the max. This is the 5-number summary. We could then do the range by 42.2 minus 0.5, right? So it's a very powerful tool if you know how to use it. Once again, press stat, choose 1 to edit, enter all your data into list 1, press stat again, scroll to the right, do calculate, and you're good to go. And you get this. Now, if you don't put your data in list 1, like I said, you have to tell it which list to use. So for instance, we already talked about this, that 10.3 is the standard deviation we want because we want for a sample. Let's say this is our set of data. Again, I've already put it in the calculator because I don't want to waste time doing that. So now if I want to calculate things, and I want to do one variable statistics, well now my data is in list 2, which means, oops, we have to change it from list 1 to list 2. You can't see it. There we go. And so you have to hit second down here, 2, because you can see there's a blue L2, and now it says list 2. So now if I go and calculate that, that will give me the statistics for list 2, which is where I put all of these numbers. Okay, so it's really simple to use a different list. You don't have to clear the first one and keep putting your data into list 1 because that's where it defaults. You just tell it to use a different list. And that way you can leave all your data in your calculator in case you got to go back and do some more calculations with it. Now with this one, if we want to treat that as a population, then we would use this bottom one, right? Because remember, Greek letters is population, regular letters is samples. Okay, so then we can say that on average, they differ from the mean by roughly 72.8 points or roughly 73 points. That's what the standard deviation tells us. All right, another skill check. See if you can find the standard deviation for that data. Okay, did you get 2.4? Or, if you round, you get 2.4. Next, we talk about the empirical rule. So this is a measure of relative standing, right? So we did measure of center, standard deviation, measure of spread. Now we're going to talk about the empirical rule, measures of relative standing. We know that if we have a set of data with a normal distribution, we're going to have a nice pretty little bell curve. It's centered at mu, which is our mean. If we go one standard deviation in both directions, that thing we just calculated, remember in Greek letters it's that little sigma, so mu plus sigma, mu minus sigma. The empirical rule tells us that if we have a normal distribution, this will capture roughly 68% of all of our data. If we go out 2 standard deviations, right, so mu plus 2 sigma, mu minus 2 sigma, that gives us roughly 95%. And if we go out 3 standard deviations, we get almost all of it, we get 99.7. That's the empirical rule, 68, 95, 99.7. So now, suppose you suspect that the emergency room waiting times for a local hospital have a bell-shaped distribution. The data have a reported mean of 116.9 minutes and a standard deviation of 56.1 minutes. Because you think it has a normal distribution, you can now identify the range of waiting times that 95% of your patients are likely to experience. And you can estimate the percentage of patients that will wait less than 2 hours and 53 minutes based on the empirical rule. Can you do empirical rules with a calculator? Not really. There's no like empirical rule button in your TI calculator that will do it for you. So you really kind of have to calculate it by hand, but I always tell my students the best way is to draw yourself a simple picture because we know what's happening with the picture, right? So here's my bell curve, right? The middle is always my mean, which in this case is 116.9. And if we go a standard deviation out in each direction, it's 116.9 plus 56.1. So you got to do that in your calculator, right? And then go out to 2 and go out to 3, and then do the same thing in the other direction. Subtract it again, and subtract it again. Okay, so here would be the measurements for each of those. Now you can see right off the bat, we know immediately that the wait times are not bell-shaped, right? We don't have a bell-shaped distribution. And how would we know that? Take a look at what we got, and how do we know? Well, if it was bell-shaped, how the heck can we have negative data, right? How can we have wait times that are negative? That's impossible. It's basically meaning that they got seen before they even got there, right? So with this, it's telling us that there isn't a normal distribution. But if we still go ahead and assume that 95%, remember, is 2 standard deviations. So it's all of this. There to there. Or more precisely, from 4.7 up to 229.1. That would be the range of waiting times for 95% of their patients. So we could basically say 95% of their patients are likely to wait somewhere between 4.7 minutes and 229.1 minutes, which is a lot of time, right? That's almost 6 hours. If we want to estimate the percentage of patients that will wait less than 2 hours and 53 minutes, we got to figure out what 2 hours and 53 minutes is. Well, 2 times 60 is 120. 120 plus 53 is 173. Aha! So they're just asking for how many are here and below. So we have to add up all this stuff. Well, it's really easy because we know that the middle, right, is at the mean, and there's 50% below this, right? So this is 50%, everything below this and 50% above. We also know that this middle piece, right, if we go 1 standard deviation in both directions, they tell us that that's 68. That's the empirical rule, remember, 68, 95, 99.7. And since everything is symmetrical, we know that we have 34 in here and 34 in here. Well, then, so now, to be below the blue line, we just have this 34% plus this 50% and 84%. So as you can see, the first solution, we get that 4.7 to 229.1 like we already talked about. And then for the second one, we can see that we can figure out that less than 2 hours, 53 minutes, what it is. And then that's 173. And it's above the mean. So by how much? Well, we do our empirical rule. We got that 34% in between the mean and that number. We know that there's 50% below that mean. We add them together, and there's that 84% I was talking about. So what have we learned? Always draw a picture. Whenever you're dealing with percentages, percentiles, the empirical rule, any of that kind of stuff, give yourself a nice little big bell curve, label everything, and then it makes the math really super easy because you can visualize what's going on. Okay, percentiles. If you divide the data into 100 equal parts, that tells you approximately the percentile that a data value lies. Basically, if you say, this is the 25th percentile, it just means that it's greater than 25% of your data. Greater than or equal to sometimes. It depends on, some people classify them as strictly greater than, some people classify them as greater than or equal to. Just know that there can be slight discrepancies that way. So that means that if Sierra received her scores for taking a mathematics placement test for her chosen university, and it told her that her score, right, was in the 61st percentile. What does that mean? Does that mean she correctly answered 61% of the answers? Does it mean that 61% of people taking the test scored the same as her? Does it mean that her score was at least as good as 61% of the people taking the test? Or does it mean that she missed 39% of the test questions? Well, the correct is C, that her score was at least as good as 61%, right? So as good or better. So at least is as good or better. So in this case, they're treating a percentile as equal or greater than. Like I said, sometimes it has to be strictly greater than. A and D are incorrect because percentile has nothing to do with how many questions you answered, because a percentile is comparing your score to all of the other scores on that test, right? It's not comparing your score to the test questions. It's comparing your test score to all other test scores. And then B isn't quite correct either, because it doesn't, B was saying like exactly 61%, right? 61% of the people taking the test scored the same. No, that doesn't mean that at all. Some could have been the same, but most likely a lot of them were less than, right? Otherwise you wouldn't have a normal distribution. You can't have 61% all getting one score. Okay? Quartiles. Well, quartile, like a quarter, just means the first 25th percentile, that is the 25% of your data, is less than or equal to the first quartile. Q2, the second quartile, is the 50th percentile, 50% of your data. What do we also call a marker where 50% of our data is below it, 50% of our data is above it? The median, right? So Q2 is the same thing as the median. Q3, the third quartile, is the 75th percentile, so 75% is less than. On Carl's recent standardized test results, the picture graph of his score showed that he was above the third quartile in language arts. His classmate said his score was at the 70th percentile, and Riley said hers was at the 79th percentile. Which of the three had the best language arts test score? Well, obviously 79th is better than 70th, and because Carl was above the third quartile, which is the 75th quartile, we just know that he was more than 75. So we know he's better than Asher's 70th, but we don't know if he's less than Riley's or better because we don't know where it is above 75. So that's all we know, is that he was above the 75th. Okay, so that's all we've got for this one.